which is composed of E1 and E2. And E1 and E2, we denote this as the basis, which is 1, 0, 0, 1. And we have also another basis S, which is composed of two vectors, V1 and V2, which are also equal to, we can denote them as 1, 2, and 1 minus 1. So we are given here two different bases, and we know that, or we know it, but let me ask you, can you say that this can serve as basis for R squared? Let me pick some more from the class here. We have Lido, Christy, Joanna. Joanna, what can you say here? Are these two bases, can they be basis for R squared? We have Esther, the next one in line. Esther, what can you say?
Yes, I think they can be used as basis for R squared.
That's true. Yes, we can use them. Why? Because the determinant of this one is different from 0, and the determinant of the matrix, which is composed of those two columns, would be different from 0 again. So both are bases. Okay. So both are bases for R squared. Then we have. Wait a second. Then assume that we have a vector v, which is 2 minus 5, or you can keep any vector. So can you come up? So Esther, can you come up with a pair of numbers?
4 and minus 2.
4. What else?
Minus 2.
4 minus 2. Okay. 4 minus 2. So let's assume that this vector 4 minus 2, it is in the standard basis. And let me give a very, what we call a standard basis is this basis, which is described by the Cartesian coordinate system, where there are x and y, they are orthogonal. Now, something that we are going to come back very soon, but since we are seeing here what are these E1 and E2, we denote them as a standard basis. For example, I'm going to erase this very soon, but imagine for R3, the standard basis of R3 is E1, E2, and E3. E1 is considered 1, 0, 0, E2 is 0, 1, 0, and E3 it is 0, 0, 1. If we're talking about R4, then E1, E2, E3, E4 would be the following: 1, 0, 0, 0. But we don't need to do everything, but you can. This is 1, 0, 0, 0, 0, 1. So let's consider if we are dealing about R squared. Let this be the standard basis. Okay. Why do we call it this way? Because the amplitude is 1. They are orthogonal. So they are. So all the amplitude is located or is projected on one traditional axis. This is R3, R4, and so on. So being this a standard basis, this is also in standard basis, because this one determines this vector 4, 2, it is projected 4 units onto this one, and minus 2 units onto this one, which if we are going to draw this one, let's see how this will look. So where is, first of all, where is 1, 0 and 0, 1? They are right here. Okay? And then 4 minus 2. Where is 4 minus 2? 4 minus 2 is 1, 2, 3. This is the x-axis. This is the y. This is 1, 2, 3, 4. Okay? Where is minus 2? It's minus 1, minus 2. And this vector 4 minus 2, it is here. Now we can always ask, do these two vectors span the board? Of course, it looks like it does. So this point 4 minus 2, that's where we had it. Now, we can ask the question which we had before why. We said that, can we write this one as alpha 1 times 1, 2 plus alpha 2 times 1 minus 1. Esther told us that we can do it because these two columns, they can serve as a basis. So we can find a pair of numbers, alpha 1 and alpha 2, that satisfy this condition. And then, let's see what are these alpha 1 and alpha 2. We can solve this using the system of linear equations. I mean, it is some work that we know very well how to do it, but we can, since this is a small system, it might be shorter if we do it just like this. So we have here alpha 1 plus alpha 2. This is equal to 4. If you can solve it before me, just do it. Here we have 2 alpha 1 minus alpha 2. This is equal to minus 2. So what we can do here, we can add these two equations. We get 3 alpha 1. This is equal to 2. Wait a second. Is it correct? Yes. And this means that alpha 1 is 2 over 3. So if this is 2 over 3, then alpha 2 is equal to 4 minus alpha 1, which is 4 minus 2 over 3, which makes this one 12 minus 2, 10 over 3. Okay? So it looks like the same vector, it is equal, wait a second, so the same vector, we can denote it, vector V is equal to, what was alpha 1? 2 over 3, and 10 over 3. But according to basis S, this is the same vector. And let's try to draw these vectors here. Where is 1, 2? The vector 1, 2, the basis is 1, 2. So here we have 1, 2. Let's draw this one in double lines, because this is the basis S. And we have also 1 minus 1. This is 1, minus 1 is here. So we have another vector, which is going to be a double line, which looks like this. So, and then, apparently, the projection of this vector V, which is shown here in blue, this specific point P, how does this project onto the 1, 2? The projection of this one onto 1, 2, it is 2/3, okay, which is less than 1, which means that if we do the best job of projecting this one down here, it would include, if we divide this vector in 3 pieces, like this, we get 2/3 of this, plus 10 over 3 of this vector, we should get this vector here. So what is 10 over 3? 10 over 3 is equal to 3 and 1/3. 3 and 1/3, it means that we can, so this is minus 1 minus 1, another unit, we're going to come down here. So this is the second one. Then minus 3 plus 3 is going to point somewhere here. So this is 3 units and 1/3. So we have 1/3 of this component. What is 1/3? It's something approximately. We're trying to draw to scale as much as possible. What is it? 1/3. So we have just a little bit like this. So if we pick up 1, 2, 3, and 1/3, which makes 10 over 3, plus 2/3 of this. What is 2/3 of this? I'm just sliding this from here, bringing it down here, and we get this much. Okay. So so this length, this is 2/3 of V1, 2/3 of V1, and this vector here, this is 10 over 3 of V2. 10 over 3 of V2. Is it clear? But of course, we can always, it could be relatively easy for us because we are very good, we know these topics very well for so far. And this is what we obtained. Okay, so this was one useful example. Yes. Let's see another example here. So let's assume we have these vectors 1, -1, 0, 0, 3, 1, and 5, 1, 2. So here, I can ask you the following question. So, what is the third column in standard basis? Now, this is almost a trivial question, but the third column in standard basis is in fact 5, 1, 2. Why is this so? 5, 1, 2. This is equal to 5 times 1, 0, 0. This is almost trivial. Plus 1 times 0, 1, 0. Plus 2 times 0, 0, 1. Now, okay, this much we know. That's good. Then let's ask the other question. Can these three vectors or three columns be a basis for our cube? So are these three vectors, or can these three vectors serve, are these basis for our cube? What can we do here? We can try to determine the determinant, right? This would be a relatively easy path. So what we can do here is we have 1 times 3, 1, 1, 2, plus 0, let's do this one also, minus 1, 1, 0, 2, plus 5, which is minus 1, 3, 0, 1. And here we have 6 minus, this is 5, this is minus 1. So here we have 5 minus 5, this is 0. So how would we answer the initial question? After Esther, we have Ermani. Ermani. Ermani.
Yes.
Is this triplet of vectors, can it serve as a basis for R cubed? What do you think?
I think no, because the determinant is equal to 0.
Yes. So we can say that the three columns, that's right, are linearly dependent. Okay, which implies that they are not a basis. So this is the line that this is how we argue, this is how we reason. But then it looks like if this is not a basis, what does this mean? This means that the 5, 1, 2, it can also be written as a linear combination of these two columns. Would you agree with that?
Yes, of course.
Yes, so we can do this one. This can be written as alpha 1 times 1 minus 1, 0. 1 minus 1, 0, plus alpha 2 times 0, 3, 1. Okay, so the question here is, what are the coordinates of this vector onto the basis composed of the first columns? Okay, this is the question. And then what remains for us is try to determine very fast what is alpha 1 and alpha 2. Now, if we look carefully at this part and this part, some of us might identify relatively fast that alpha 1 is equal to 5, right? We can see it from here. And alpha 2 is equal to 2. Because you see from the third equation that alpha 1 times 0 plus alpha 2 times 1 will be equal to 2. So this means that we can write this one. Let's write it like this. This is equal to 5 times v1, or Actually, v1 I mean the first vector which is over there, but let's write the whole thing. This is 5 times 1 minus 1, 0, plus 2 times 0, 3, 1. So then we can say that this vector here, vector v, which is equal to 5, 1, 2. In fact, this is projection onto the standard basis. Let me do it like this. When we write nothing here, we mean we're talking about the standard basis. Okay? So our standard basis, we don't write it. But this is also equal to what? This is equal to what is this? 5, 2 according to basis S. Okay, so this is what this vector is. Now, basis S in this case, let me write it here. Basis S is composed of by 1 minus 1, 0, 1 minus 1, 0, press here, and then we have 0, 3, 1. 0, 3, 1. Okay? So this is how we can write down the coordinates of a specific vector on a certain basis. Okay. I hope we are clear in these. Let's move to another material. Okay. Then the next topic we're going to talk about, we're going to mention dimension. Now, dimension. So the initial. So regarding the dimension, what we can say is that any vector space V vector space can have infinite number of bases. Okay, so we can find an infinite number of vectors which can describe correctly this specific space. Okay, then because what we mean is that you can pick up this is a basis for the R square, right? Then this one is also a basis for R squared. Then this one is also. Then this is also. This is also. So you know that this is also a basis. So if you change this angle by 1 degree or half a degree, you have a new basis. But all of these bases have the same number of vectors and are composed with the same number of vectors. Okay? So what you mean with this one is that if this is R squared, we should have only 2 vectors. We cannot have 3 vectors. This is R squared, this is also 2. Because the basis is composed of the minimum possible number of vectors that can describe every point. Okay? And then, as a theorem, we can write this down as a theorem, which states that let V be vector space with basis B, which is equal to the linear combination of V1, V2, V3, Vn, composed of n vectors. Okay? Then then any set of n plus 1 vectors is a linearly dependent set, okay? So this is essential, which means that for r squared, if we have here 1, 1, minus 1, 3, this is a basis for r squared. But what about this, if we have a set which has also 4, 5? What is this set? Is this a linearly dependent set or independent? This is dependent because the first two, they constitute a basis, which means 2 are enough. But if you include 3 vectors, then for sure, this is a linearly dependent set because the 4, 5, it can be written as a linear combination of these two. So where is the basis? So this is, let me do it like this. In fact, this is a basis, which means that picking up the first and the third, it is a basis, which means that 1 minus 1, 3 can be written as a linear combination of the other two. So we can write it like this. Minus 1, 3, it can be written equal as alpha 1 times 1, 1 plus alpha 2 times 4, 5, right? Now, we can do this, but at the same time, we can also say that 1, 1, it can be written as alpha 3 times minus 1, 3 plus alpha 4 times 4, 5. Okay, we agree on this one, which means that we are using the first and the third as the basis. Good. We are using here the second and the third as a basis. This is also possible. But at the same time, we can use the first two as basis. But so this is equal to alpha 5, 1, 1 plus alpha 6 minus 1, 3. So these are all possible. And now the number of vectors. So now we give the definition. This is the definition of dimension, which is the following. The number of vectors in the basis is called the dimension. Okay? So the number of vectors in the basis is called the dimension. It is not that we have not seen this before. We know, for example, that sometimes we solve a system of linear equations, we find a unique solution, there's only one point. We have said before that it is dimension 0. We find a solution of a linear system of equations, we get a solution, a line, and that one is called, we call it one dimension. Sometimes we used to find the solution of the system of linear equations. It was a plane described by two vectors. We used to say, because it's also intuitively, we can also find it by intuition, the dimension of the plane, which is described by doing linear independent vectors, it has a dimension of 2. Sometimes the null space can be composed of as a linear combination of 3 vectors, then the dimension of the null space or any solution space would be equal to 3. But here we are also providing the formal definition as it's written on the board. So these 3, this is the definition of the dimension. So one thing which is extra here is that we define, if we have a vector space which has, so any vector space V, which includes the 0 vector, this is defined as having dimension is equal to 0. Okay. Now, Rn, this is has a basis of size n. Which means that dimension is n. Okay. So a plane in a three-dimensional space. What is the dimension of a plane in R cube? the dimensional plane, which can be found in the three-dimensional space, it's equal to 2. Okay. Okay, so let's look at a formal definition, but for the sake of space, let's say that, let me erase this one. And if you haven't seen this yet, that we have this dimension here is equal to 0 by definition. Now, let's assume that we have a matrix A, which is A m by n. Okay, and we know what this looks like. It has m rows and n columns. And regarding this one, we can define a few spaces. We have the row space, which by definition, this means that the linear combination of the rows, it constitutes the row space. And this one is called, as linear combination of Ri. You can write this one of the rows, right? We have also the column space, which is the linear combination of Ci. Then we can also have we have another space which where we are used too much with it, which is the null space. Now, null space, we know what it is. It is a set of all vectors such that Ax is equal to 0. We have also the row space, the column space, and the row space. And one thing that we can look at is the following. The row space, is it a subset of which space? The row space, this one. Let's consider this one Rs. This is a subset of what? R what? Rm or Rn? Сифтомио. Edvisi, what do you think, Edvisi? Edvisi? So, what the answer is going to be whether an Rm or Rn. So, which one would you select? So, a row, we have m rows, but n columns, which means that each row has. So let's think about this one. 1 minus 1, 3. 2, 5 minus 1. This is a 2 by 3 matrix, right? 2 by 3. So the rows, this is a row, and the row, it is a subset of R3 in this case, right? Which is going to be this element. And the column space, which we can denote this one column space, this is a subset of what? So 1, 2 is a column, minus 1, 5 column, 3 minus 1 is a column. And all of these include, they are defined by a pair of numbers. So this is R squared. And now, the null space is a subset of what? Actually, sorry, I should write this one Rm in the general sense, but the null space of A is a subset of what? So, let's think for a moment. A, n by n times x, which is n by 1, it looks like Rn. Because null space of A, it is the union of these vectors, and these vectors apparently are n by 1. So all of these three spaces, which can be associated, which are associated to any matrix, to any combination of numbers, we can define those three sets that we see, which is the row space, column space, and the null space. Then, let's move on. Now, it's always good to move with examples, because we will try to make clear what we have. Now, since the row space, this is not a new concept. Column space also, we have used this a lot. But what we want to discuss now in a formal way is how we can find the basis of the column space, row space, and the null space. Now, let's look at this example. Let's assume that A is a matrix which is 4 by 5, and this is defined as 1, 0, minus 1, 0, 1, 0, minus 1, 0, 2, 1, 3, 1, 2, 1, 3, 1, 1, 2, 9, 2, 1, 2, 9, 2, 1, 1, 1, 0, 2, 4, 9, 1. So this is our matrix 4 by 5, okay? Now, we have some numbers which are put in this matrix. It might be a little difficult to figure out right away what is the rank of A. Because if we know the rank of A, we can determine how many rows are linearly independent and how many are dependent. Also, it might be difficult for us to figure out what are which columns are linearly dependent or independent. And by the way, we can have a look at the columns. The columns, so if we see here, the columns of this matrix are Ci, they are a subset of R what? Let me ask here the LT. LT? The columns of I.
4, sorry.
4, okay, I wrote it, sorry, before you open the microphone. So the columns of I, of this matrix, they're a subset of R4. But now, what do you think regarding the columns here? How many columns do we have?
5.
We have 5. Now, for R4, we need four vectors, right, to be linearly independent. But we have 5. We can right away say that all of these columns, they are linearly dependent with respect to each other, right? Because we have more vectors than we have dimensions. It's like having 3 vectors in 2-dimensional space. For sure, they are going to be linearly dependent. There is no way. Okay? We can even have this one, 1, 1, minus 1, minus 1, 2, 2. They are always linearly dependent, but we're talking, even if we randomize them as much as possible, if we throw dice, just say them Zara, as a sort of operator, if we mix up 6 numbers in 3 vectors, where this will always be linearly dependent, because the R squared, all it needs is just a pair of vectors. Now let me take this away. But now, let's see how we are going to determine the spaces.
Professor,
Yes.
I have a question.
Yes.
Can you explain again how are you defining the subsets for the columns and the rows? Like here you said that the columns Ci is a subset of R4. Can you explain how you get that number again?
Yes. So you read for me one column. Tell me that one column. I'm going to write it.
A random column or a column from the... Okay, so 1, 1, 1, 0 maybe.
1, 1, 1, 0, right?
Yes.
Now, how many values are you using to describe this vector?
4.
Okay, that's R4. Okay.
So about the column space and the row space, this is how you do it.
Yeah, I mean, yes, now, for the moment, you are just asking, what is the dimension of this one? And I see that the column is composed of 4 numbers, so it is subset of R4. If we look here, what did we say here? The columns here, they have 2 entries, so it is a subset of R squared. But here, I made because in order not to get confused or to make this a little better to understand, I just wanted to make it easy how you determine these, right? I don't know, is it clear now?
Yeah, thank you. So if you want to find the dimension for the rows, you do the same. You see how many entries they have.
Yes, that's correct, yes.
Okay, thank you.
Edhe shikoj diçka do. Unë personalisht më gjithmonë i ngatroj. Në fjalë po të mendohem që i gjatë e gjej. Por gjithmonë ajo që mund të ndihmoj është kjo. You have here the general definition is A n by n, right? Shkruaj një matricë nuk është katrore, bëhet 2/3, okay? Shkruaj 2/3. Edhe here row space is a subset of what? Kush është jeshtë këtu? Është 1 minus 1 treshi. Sa vlerë ka 3? Ku është treshi? Këtu. Ku është n këtu? E është këtu, okay? Më kupton më?
Po.
Shkruaj column space. Shkruaj një matricë 4/5, 2/3. Thjesht për ta dalluar që kush është kush. It's not difficult to think that rows, we have m rows and n columns. If you have n columns, that means that the row has n entries, right? So the row space should be R. So you can also mund ta nxjerrësh edhe nga një logjik pa vendosur numra. Po vendosësh numra, mund ta gjesh pak më tepër. Kupton?
Po, kuptoj.
Okay, so now let's take it away and let's see what we obtain. So to figure out what are the dimensions of the row space and column space, let's say also something. We have 5 columns. 5 columns, they are R4. For sure they are linearly dependent. And what is the dimension of the column space? The dimension of the column space could even be 2. If we have only 2 linearly independent vectors here, if we have only 2 linearly independent columns, then the dimension of the column space is going to be 2. If we have 3 linearly independent columns, the dimension is going to be 3. Or, imagine for a moment, we have here 1, 0, minus 1, 0. If the second column is the first column times a constant number, if the third column is the first column times a constant number, and again, then the dimension of the column space, it is going to be simply 1, because we have only one linearly independent, and if the rest are multiples of the first column, that means the dimension is 1. Similarly, it can be 2, we have 2 and 3. But now, let's move ahead, and what we do here regarding the row space and the column space. First of all, the row space is equal to the linear combination of the 4 rows, okay? How we write it is this. We get here the first row, 1, 2, 1, 1, 2. The second row, it is 0, 1, 2, 1, 4. The third row, it is minus 1, 3, 9, 1, 9. And the fourth is 0, 1, 2, 0, 1. So this is our row space, okay? It's not a mistake, but we have not, there could be also some linear dependencies in between. And we can figure this out by calculating the reduced row echelon form of the matrix A. It's not
Professor, I have a question, Professor.
Huh?
Kam një pyetje profesor, nuk mund, do të thënë kjo bësh vetëm në rast se këto janë linearly independent, apo?
Kjo këtu?
Po.
Po, shiko, këtë mund ta shkruaj.
Nuk e problem që është linearly independent, apo e marrim më assuming.
Jo, këtu ke shumë të drejtë. Kjo është teknikisht e saktë. Dhe ne thjesht po shkruajmë për shembull edhe column space. Në column space është përbërë nga kjo, por nuk kemi thënë akoma që kjo është baza e kësaj, dakor? This is not the basis. Kështu ke të drejtë, kritika shumë e vend, edhe është ajo që duhet ambino, faleminderit, por për të kuptuar edhe për çfarë po flasim që row space në princip është kombinimi i këtyre. Tani shikojmë kush është baza, nuk i kemi thënë nëse, shikoj ambino të diçka. Row space i vetë është subset i rëpesis. So, row, let me write it like this. Row S, it is a subspace of R5, right? Sorry, R5. Pse? Se që duhen 5 vlera për çdo kolon. Për kjo është R5. Por nëse ne kemi, albino më përgjigj tutën këtu. Nëse ne kemi 4 vektorë, sa ka dimensionin RS-ja?
Nëse kemi 4
Kemi 4 rreshta. Sa është dimensioni?
Në 4 rreshta 4 bie.
4, ke drejtë albino, ke 4. ne akoma nuk kemi llogaritur kësaj reduced row echelon form. Është 4, po mund të jetë më e vogël se 4. Sepse deri tani ne kemi aq shumë eksperiencë duke zgjedhur sistemet e ekuacioneve lineare, që çfarë bëjmë? Punojmë me këto, bëjmë atë reduced row echelon form, gjejmë hipotezën, shpesh ne mësoj që shohim me 0 në fund. Nëse këtu në fund na dalë me 0, dimensioni i saj do shkojë deri te 3. Dakor? Besoj që pjesa e qartë. Okay, pra deri tani, po çfarë kemi kujdes, row space is subset of R5, okay, but we have only 4, which means the dimension could be 4 in case the reduced row echelon form gets for us a full row of zeros, the dimension is going to be 3, so we can write this one so far. But with all your intervention, you are completely right. And then let's move on, and we can also say at this stage that the column space of A, which is also defined as range of A. I believe we remember that whenever we have AX equal to B, the B is always a linear combination of the columns. So I believe we can write here column space of A is equal to the range of A, and in principle would be equal to writing down all the columns 1, 0, minus 1, 0. And I'm going to write the same thing, but allow me to skip maybe 1 or 2 steps. First, second, third, fourth, fifth. Let me write the fifth column is going to be 2491. 2491. And this is the column space. We are skipping one here and one here. But still, we could even simplify because we have never tried to look in detail. So what is the next step? Traditionally, this is what we get. Actually, it doesn't look good being like this. 1, 2, 2, okay. And then all ones, a 0 at the bottom, we did it. Now, let's see what is the reduced row echelon form of A. This is what we should be looking for. And the reduced row echelon form of A, we get 1, 0, 0, 0, 0, 1, 0, 0, minus 3, 2, 0, 0, 0, 0, 1, 0. So we have a leading one, which means that the leading ones, they are full of zeros in their column. The column leading ones, they are alone. So this is the leading one, and then we have here 0, 0, 1, then we have 3, minus 3, 1, 3, minus 3, 1, 3, 0. So this is the reduced row echelon form. If we want to keep away all the possible, okay. So below the red line is all of zeros. What is the rank of A? From here we see that the rank of A is equal to 3 because we have only 3 rows which are linearly independent. Immediately, the discussion that we had with Albino just a few minutes ago, we said dimension is smaller than 4. Apparently, dimension is of the row space is equal to 3. Okay, both are true. And so the row space of R is now we are going to correct our initial predictions. So initial prediction was this, right? And or would you allow me to do it here? So I'm going to erase this one. We don't have very fundamental information, so we're just discussing about the dimensions. And what we can say is that the row space of matrix A, so the row space, this is going to be equal to the linear combination of which rows? We are going to consider the first row, the first, the second, and the third row. Okay, this is what we are going to consider. But we can also pick up, and probably we should, we can consider these as the vectors which can span the whole space. So here we can write 1, 0, minus 3, 0, minus 3. Then we have 0, 1, 2, 0, 1, 2, 0, 1. Then we have 3 zeros, 1, 3. 1, 2, 3, 1, 3. So now this is more clear. Normally, we write this linear combination of these when we are talking about the basis. Ракеш база. Subvectorial trap. Dimensional row space, check out trap. Okay, so this is the basis. And we picked up only what's the name? The simplified or the small, not simplified, how can I say? Yes, we can call it simplified because we added a lot of zeros to the rows. Okay, so
Professor, the reduced row echelon form that we wrote down there, is that just row echelon form or reduced row echelon form? Because I don't think
this is a reduced row echelon form. Now let's write down the column space. The column space is going to be equal to the columns where we have the leading ones, okay? Because this column does not have a leading one, so we're going to pick column 1, column 2, and column 4. C1, C2, and C4, which is also, we can write that column space is equal to the linear combination of column 1, 1, 0, minus 1, 0, C2, 2, 1, 3, 1, 2, 1, 3, 1, and we jump, we skip the third, we get the fourth, 1, 1, 1, 0. So this will be the column space of the matrix A. So this is how we're going to pick them up.
Professor, why did we skip the third column?
We see the third column because we are going to consider only the columns that have a leading one. So if you look at these.
Okay, thank you.
Okay, yes, sure. You're welcome. Okay, this is 6, 7, 6, 8. Now we have also the null space of A. So what is the dimension of the null space of A?
Professor, I have a question.
Yes.
At RS equals linear, and you took the vectors from the reduced row echelon form, while at CS you took it from the original vector. Why?
You mean here, right?
Yes,
This
you
is
took
a,
those vectors from the original one, and at the RS you took it from the reduced row echelon form.
This is a good question, and this is the difference between row space and column space. The row space, we can pick these because we obtain these by playing with the rows, okay? And this is equivalent to this one. Let me say the following. So let's assume we have 2x plus y is equal to, how can I say this, is equal to 6. And then we have also 22x minus y is equal to 7. Okay, I'm just putting up some numbers. Now, we can combine these two rows, okay? We can combine these two rows and we get 24x just by adding them. This is equal to 13, right? Because they cancel each other. So, this remains true because we were combining the rows, but not the same, it will not be for the columns, okay? So, in principle, since we're doing row operations, we can keep up the updated ones because the moment we keep adding, potrei duke mbledh, duke zbrit, rresht në njëra tjetrën, ai informacion i rresht edhe prapë, nuk po humbet. Ne vetëm po I thjeshtojmë. So we are reducing that, so we are producing a lot of zeros, we have the same equations, so we say that if we were solving an equation, which means that here we are multiplying this one by x1 down to x5. And we want to solve this one also similarly, x1 down to x5. If we solve the system here or here, the solution x1, x2, x3, x4, and x5, it will be the same, right? Why? Because we have just simplified the rows, and this is why we can use the rows. But not the same is happening with the columns. So that's why for the column space, we read them from here, from the row space, we can read them here. Is it clear?
Pra row space-in mund ta marrim nga të dyja, s'ka rëndësi se flitin informacion kanë.
Shumë e drejtë, po.
Ndërsa column vetëm nga origjinali.
Po, column dhe marrë original, ne humbim atë esencën e column. E qartë është?
Okej.
Profesor, edhe një pyetje për këtë çështje. A prish punë për shembull nëse e përgjigj column space prej matricit origjinal, do me thonë pa e kthy në reduced echelon form, row echelon form.
Ti po thua për column space, ë?
Po, për shembull, do me thonë nuk I marrim ato për column space prej matricit origjinal, po I marrim prej RREF.
No, that's wrong. You cannot do that.
Pe kuptoj që është gabim, po a mundesh me argumentu pse?
Prita më pak. Because, yes, I have to do it. And this is a beautiful question. Let's think about this one together now. The thing is that if we pick up these, we see that we are having E1, E2, and what is this? E3. And with these, we're picking these out of R4. Now, sorry, if you remember, standard basis in R4, we had E1, it was this, E2, the second element is 1, E3 is 0, 0, 1, Charge Kata is 0, 0, 0, 1, right? So we are having only these vectors, but the issue is that we cannot, let me try to find you a good excuse for this. Okay, now I think I found it. So let's assume you come to the exam and Albino is going to pick these as a linear combination for the column space, right? Albino picks this. Yulium says, no, you gave us these rows for the basis. I'm going to pick these as a basis. You do it, and then I ask you to do this. I say that write for me column 5 as a linear combination of these columns here. Can you do that? Your question is an excellent one, and I thank you. But now I'm saying this. You have a column 5, which is C5, which is equal to 2491. 2491, okay? And now, here comes Young's solution, who says that this is equal to alpha 1 times, I'm picking up the columns from here, which is 1, 0, 0, 0. Do you see the problem, Luke, or shall I continue?
Yeah, it's visible. It's good.
Okay. I just wish we have more questions like this in the future forever. You are in the first year. We're going to see each other until you graduate, especially with me. We'll see each other a lot. So this is the best you can do, Luke, okay? Then Albino comes up and says, you know what? I can write this like this. I say A4 times 1, 0, minus 1, 0, plus alpha 2. Sorry, this is alpha 5. Let's assume that this is just another alpha, plus alpha 6. 1, 1, 1, 0. Now, can you find a solution here?
No, if we would have another one,
Yes.
another term, let's say, yeah, to get that one that you just circled.
That's correct. So you cannot get this. Yeah.
Okay, so we can't do it because we are deficient, let's say, we don't have enough terms.
Yes, that's correct. But Albino can do it. He can say that, well, I have the original columns. I can make up for this one, and even you cannot even C2 is a problem. So you can write also C2 creates some issues because C2 is not included because here we have skipped, we have taken away C2 and C5, and we should be able to write these. And C2, actually C2 and C5, they both have a non-zero term here, which creates problems, right? Okay. Now, okay, this was a good question, but now I want to ask you again, how many free variables do we have here? How many free variables do we have here in the reduced row echelon form?
Two
I
free
think
variables.
there are 2.
So wherever we don't have a leading one, these are 2. So it looks like free variables. It is C3 and X3 and X5.
Yeah.
And if we solve the system, we are going to see that, let's take this away, X1, X2, X3, X4, and X5, this is going to be equal to S times 3 minus 2, 1, 3 minus 2, 1, 0, 0, plus T times 3 minus 1, 0, minus 3, 1. So we did not solve it in detail, but it includes, or you know how to equal this to 0. And since we have 2 free variables, we can say that the dimension of, what is the dimension of the null space of A? This is equal to 2. So if the dimension of the null space of A is 2, we can say that the nullity of matrix A is equal to 2. This is nullity. This is equal to 2. And then we have a very useful theorem, which is called the rank nullity theorem. I need some space on the board to write this, and then for this, I'm going to take out this question that you asked me lately, because I want to leave the rest. And the rank nullity theorem
Professor, I'm sorry to interrupt you, but Professor Joanna posted on Classroom for a makeup class, and I don't know, or isn't
did Professor Joanna call you for a makeup class?
yes.
Give me 1 minute, let me write this theorem, and we'll give a break and we can discuss it in detail. So the rank nullity theorem, we can say that the dimension, the rank of A plus the nullity of A this is equal to n. So this is what the rank nullity theorem, and here n, we know what n is. N is the number of columns. So in principle, so even if we see here, what was the dimension of the row space? It was equal to 3, right? Because we see this, actually the rank is equal to the number of rows that have leading ones, so it's going to be 3. In this example it was 3. How many free variables did we have? We had 2. So in this case we have 2. And this means that this is 5, and 5 is the number of columns. So this is a theorem, it's called rank nullity theorem, and for all the examples that we have solved so far, you are always going to notice that this is the case, okay? Now we can give a second break.
Please. How did nullity equals to 2 in the previous example?
Because that's a good question. Because nullity, it is defined as the dimension of the null space. Okay, that's a new definition. Okay, so nullity is it's an indication of how much does the null space span? How much what dimension is it covering in space? We could have an example where the null space can be described as a linear combination of 3 vectors. Then the dimension of the null space would be 3, and the nullity of A would be 3. Is it clear?
So the nullity is the number of rows that don't have leading ones. In other
No,
words.
no. The nullity is not that
Number
way.
of columns, sorry. Are
Wait
not
a second. These numbers, I believe, all of us, we know that we obtain those when we try to solve the system equal to 0, right? I don't know, am I clear? Or is there anything else I need to clarify?
Jo thjesht desha me gjetë profesor si e kemi gjetur nullity me 2, do të thonë unë e mora sikur, do të thonë tek kjo që kemi bërë row echelon form, kemi dy do të thënë dy kolona që nuk i kemi leading ones, edhe mendova se mos kjo ishte nullity.
Jo, është kjo, po nullity ajo është, shiko pa. Ato numri i free variables, të cilat se free variables quhet kjo këtu, edhe kjo këtu. Që do të thotë kjo është x1, x2, x3, x4, dhe këtu ne kemi që x3 dhe x5 janë free variables, këto të dyja. Dhe për të zgjitur sistemin, me këtë operacion gjithë me 0, sa 0 do kemi këtu? 4, 0, 0, 0, 0. Sepse kjo është 4 me 5, okej, 4 me 5, kjo është 5 me 1, kjo është 4 me 1. Dhe tani, për free variables kemi vetëm dy conë. Për i themi x3 i themi që barabartë me s. Okej. Dhe kush është tjetër? x5 është barabartë me t. Pra, po të zëvendësojmë këto vlera aty në sistem, këtë do gjejmë. A ka nevojë ta sjellim këtë për shkak për të parë se si del kjo?
Jo, s'ka nevojë pas.
Okej, sepse thjesht i reminder, në
Nullity ne mund ta përcaktojmë me këtë numrin e free variables.
Eksakt.
Ende.
Shumë e drejtë. Në rregull. Në pyetje tjetër?
Profesor, në qoftë se kemi mbaruar me pjesën e mësimit, mund të sqarojmë diçka për midtermin?
Do e bëjmë sa të